We're continuing with the pre-algebra chapter in the algebra textbook. In this video, we're going to go through the fourth section, which is on polynomials and multiplication of radicals. Okay, so in algebra, different types of variable terms as well as different types of variable expressions are put into categories. And so you're going to need to be able to look at a term, an algebraic term, or look at an algebraic expression and identify the category that it falls into. Now, this can get a little confusing, but I've come up with a way that I want to approach teaching you this as we go through these opening chapters that I think is going to work very well for you and make it a lot easier to memorize these categories and easily identify what category any expression or equation is in. Okay, so the first thing that you need to remember is that so sometimes it's easy to think that, wow, there's so many different operations on variables. There's so many different ways you can operate with variables, but in reality, your mind is just playing tricks on you. There's not nearly as many fundamental operations on variables as you think there are. So, okay, think about it. Up to this point, so okay, we have a variable. We know what a variable is. This is just a placeholder that represents any number. A lot of times we just think about it as any real number, but this could be a placeholder for any complex number as well, any number in the complex plane. Okay, now as far as the fundamental operations we can apply to this variable, as far as what we've learned up to this point, it's just, okay, raise it to a positive integer exponent, raise it to a negative integer exponent, or raise it to a rational exponent, which is, this is where the radical comes in. Okay, and that's it. That's it. I mean, yes, there is addition, subtraction, multiplication, and division, but that's not new operations in the sense that, you know, okay, yeah, we could add x and x cubed, but that's not like addition, subtraction, multiplication, and division are operations between variables. Okay, and as I've mentioned before, another thing to note is that, like, x cubed, okay, x cubed, yes, that is like its own unique operation, but inherently this is multiplication, right? This is just like some packaged form of multiplication. And a root is just the opposite of this. So this is like about multiplication. And even when we get to logarithms and exponentials, which are the other two operations we're going to learn in this entire course, that's just has to do with multiplication as well. Like an exponential is just a base like 2 to the x power, where you're just multiplying 2 by itself x times, right? So it's all addition, subtraction, multiplication, and division. Fundamentally, that's all we're doing with numbers here, okay? And then again, as far as just an operation to a single number, a single variable, we take it to a positive integer power, a negative integer power, or to a rational exponent power. That's all we've learned so far. And it's close to all we're going to learn. I mean, we still have to do, what about an irrational exponent power? But after that, that's it. Until we get to exponentials and logarithms, and then that'll be it. Okay, so you can see that there's really not that many fundamental operations that we're doing to variables in algebra, in all of algebra. It seems like a lot, but it's really not. Okay, so with that, one category that we can put any expression, so an expression could be just one term or a sum of terms. Okay, one category that we can put any algebraic expression into is the category of polynomial. Okay, and before we go through this definition here, let me give you an informal definition, a really useful and intuitive informal definition. So, okay, a polynomial in any number of variables. So you can have a polynomial expression in just one variable, like a polynomial expression in x, or in any number of variables. That just means the total number of different variables you have in the expression. Okay? So you can have a polynomial expression in 3 variables. So you've got like 3 terms, maybe you're summing up 2 terms, but overall there's 3 different variables. What that means, if it's a polynomial expression, what that means is that every single variable is going to be raised to some whole number power. So a whole number is the positive integers, but also 0. So yeah, I mean, you could have a variable raised to the 0 power, then it just turns into a constant. But like in general, what you're going to see visually is every single variable in the entire expression is going to be raised to some positive integer power. Then you call that's a polynomial expression. You're dealing with a polynomial. Okay, so 1/2 x squared y minus 2zg plus 4/3 k to the 4th x. Okay, here's an expression, right? An expression is just some sum of terms, of algebraic terms. Okay, now like even if, it's not like if these variables could potentially represent, be placeholders for complex numbers, this would change. This applies in any situation. So these variables could be placeholders for any complex number in the entire complex plane. Okay, well, we look at all the variables. They're all raised to positive integer exponents. 2, 1, 1, 1, 4, 1. I mean, like the idea would be, let's say we added a constant at the end, 5. Oh, well, that has an x to the 0 in front of it. That's kind of the idea with a 0 power. Okay, well, okay, this is a polynomial expression then. This is a polynomial expression, and to be more specific, we've got how many different variables? 1, 2, 3, 4, 5, 5. So this is a polynomial expression in 5 variables. That's it. Now, if just one of these variables has an exponent that's not a positive integer exponent, which would mean there's only 2 other options in that case, that would be a negative integer or like a rational exponent, or like, we haven't learned this yet, but like something like pi, like an irrational number exponent, then it's not a polynomial anymore, just one. Like, but you could have this. Okay, so this entire expression now is not a polynomial expression, but then you could just focus in on these 2 and say, okay, well, that's a polynomial expression, or you could go term by term. You have a polynomial term. Okay, so that's the idea. That's the idea. Okay, now let's read through this official definition they give here, and we'll learn some other terms. At the start here, they just give an application example, but then they just repeat everything here with the official definition. So, okay, a polynomial in the variable x. So this is a polynomial in a single variable x. I guess we could have said that we had a polynomial in variables x, y, g, z, k. We could have said with that expression. You could like list out the variables. So here they're talking about a polynomial in just a single variable x is an expression of the form. Okay, so you got a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2, and then plus dot dot dot, then a sub 1 times x plus a sub 0. Okay, the coefficients, the a sub n's coefficients are real numbers. Okay, but we can think about since complex numbers are constants, right? We look. This is not a variable. A complex number is not a variable. It's a number. We can think about. We're allowed to have complex coefficients. We're going to talk about polynomials with complex coefficients in chapter 3. So, but they're just trying to. Right now, they haven't introduced us to complex numbers in the textbook yet. So, but okay, they're saying that these are real numbers, the coefficients. But again, just like 2 is a constant. 2 minus 3i is a constant. 5 plus 4i is a constant. These are all just numbers, not variables. Okay. All right. Now, but a sub n is not equal to 0, and the exponents, the n's, n minus 1s, n minus 2s, are whole numbers. You see? So, I mean, that's this is the big criteria for a polynomial. This is the enormous criteria, that you've got all of the variables are whole numbers. That's the enormous criteria. And the one you need to sear into your brain. Every single exponent has to be a whole number, or else you don't have a polynomial expression. Okay, now the term a sub n times x, this term here is the leading term. The coefficient of the leading term is the leading coefficient, and the exponent n is the degree of the polynomial. So yeah, they're saying that a sub n can't be 0. So these other coefficients are allowed to be 0. Like you could have, what they're saying is that you could have 3x to the fourth minus 2x plus 5. Right? Well, in this case, we've got the x, there's no x cubed term, there's no x squared term, but you can think about it like this. Right? The coefficients on those terms are 0, is what they're saying. But like a sub n, the leading coefficient, can't be 0. That doesn't make sense for the definition. If you're allowing the leading term coefficient to be 0, well then that doesn't make it, you can't make a definition. If you're going to have so we're going to call this the degree of the polynomial is the degree of the highest term, is the largest degree. So this polynomial has degree 4. Well, okay, if we're going to have a degree 4 polynomial, we can't have a leading coefficient equal to 0. Otherwise, I could say, well, this is a 5th degree polynomial, right? That wouldn't make sense. So the leading coefficient, the nth term, the highest degree term, can't have leading coefficient equal to 0, but the other coefficients can be 0, like we see here. Okay, and then you look at this kind of like this is 5 times x to the 0. And so, yeah, what they're doing then is you've got so this polynomial has degree 4, so n is equal to 4. So a sub n, or I'll call it 4, a sub 4 is equal to 3. Okay, so then a sub 3 is equal to 0. That's n minus 1. You see, n minus 1 is a sub 3. A sub 2 is equal to 0. A sub 1 is equal to minus 2, and a sub 0 is equal to 5. The leading coefficient is 3, and the degree is 4. And so you just count down, like you start with the degree term. So you start with a sub n times x to the n, and then you just keep going, then you go n minus 1. So we went to the a sub 3, x cubed. Then a sub 2, x squared, right? 4 minus 2 is 2. This is n minus 2. And then we went all the way down to a sub 1 times x to the first, and then a sub 0 times x to the 0, which is the constant. Okay, and then, yeah, again, this is the leading term, and this is the leading coefficient. All right, so that's the notation for a polynomial in a single variable. Okay, now some more notation. Let's see. They just give an explanation of why those letters are used for the definition. Okay, so a polynomial with one term is called a monomial. A polynomial with two terms is called a binomial. So yeah, you can have a monomial. You can have like 5x squared. That's it. That's a polynomial of degree 2 with the leading coefficient equal to 5 against degree 2, and then the a sub 1 equal to 0, a sub 0 equal to 0. It's a monomial. Now, but you could even have but technically, the number 1 is a monomial. The leading coefficient, this is degree 0. The degree of this polynomial is 0. A sub 0 is 1, and that's it. The degree is 0. And the leading coefficient is 1. Okay, a polynomial with two terms is called a binomial, and a polynomial with three terms is called a trinomial. So monomial, binomial, trinomial, those are 1, 2, and 3-termed polynomial expressions. Okay, now let's see. It says some polynomials have more than one variable. Yes. So this is a trinomial in x and y. That's what you would call this. Now, there's some more terminology that we can use for multivariable polynomials. So, like, how do you classify the degrees of these terms? You know, because you want to put, as it mentioned, you want to put, it's the most organized form is to put the polynomial in descending order of degree. So you want to order the terms in descending order with the highest order term first. So how does the degree of the polynomial come into play with multivariable polynomials? So what you do is you just like, okay, this term here. Okay, the way you do it is you just add up the degrees of each of the variables. So this would be this whole term would have a degree of 11. That's the idea. Then, so let's see, they've got. Then this next term would have a degree of 7. This next term would have a degree of 5, and so they put it in descending order of degree. So minus 4 x to the 4th, y to the 7th, plus x squared y to the 5th, plus 5x y to the 4th. So yeah, it's in descending order of degree. This would be, you could say this is a trinomial in x and y with leading coefficient minus 4 and degree 11. And that gives a good description of this expression here. Okay, now adding and subtracting polynomials. Well, this, you can think about how this is going to be pretty straightforward. The only kind of challenge here would be you have to know how to identify like terms. If there's like terms, combine them. If there's not, then just leave it as it is. That's it. It's just combining like terms. So if we're going to add these two polynomials here, well, what are the like terms? You've got the w squared. There's these two terms are like, minus 5w squared and 8w squared. The 6w and the minus 4w are like, and then the 3 and the 2. So let's see. You'd have minus 4w cubed isn't going to be able to combine with anything. Then minus 5 plus 8 is going to be positive 3. Then 6 minus 4 is going to be positive 2. And then 3 plus 2 is going to be positive 5. And there we go. Okay. Now, yeah, and you can see those are two polynomials, right? Look at all the exponents, all whole numbers. And same here. This is these are multivariable polynomials, but they're all whole number exponents in the variables. So, okay, yeah, I mean, we have so 6.1 a squared b, and then you have this 2.6 a squared b, but you could just distribute this minus sign to start. So 6.1 a squared b plus 2.9 ab minus 4.5 b squared, and then minus 2.6 a squared b plus 4.1 ab minus 2.1 b squared, and just combine like terms. Easy. Okay, now multiplying polynomials, well, this is going to be straightforward as well. If you're multiplying two monomials, well, then it's like just the properties of exponents, right? If we've got these two, 4 minus 4x squared y to the 5th times 1/2 x cubed y. Well, I mean, yeah, you take advantage of the associative property. You can just bring the like terms together and use the properties of exponents. So minus 4 times 1/2 is minus 2. X squared times x cubed, just add the exponents. Y to the 5th times y to the 6th, done. Okay, now, but if you're multiplying, non-monomials together, then you're just going to need to use the distribution properties. So, but still, not a big deal. You just use the distribution property, and then you're just multiplying different monomials together. So it's easy. Right, so just distribute. Minus 3x cubed times 4x squared is going to be minus 12x to the 5th. Minus 3x cubed times minus 2x, you're going to have positive 6x to the 4th. Minus 3x cubed times 6 is going to be minus 18x cubed. Okay, now multiplying polynomials with two or more terms, this is still just a distribution property. Okay, so you need to know how to distribute. This has nothing to do with polynomials. This is not inherently married to polynomials at all. I mean, all numbers, no matter what it is, obey the property of distribution. So how do we distribute here? Okay, 4w times 2w is 8w squared. 4w times minus 3 is minus 12w. Okay, now we do 7 times 2w, and then we do 7 times minus 3, like that. And now, okay, 8w squared minus 12 plus 14 is positive 2, like that. So that's just distributing. And again, this has nothing to do with, this is not inherently about polynomials at all. All numbers. So any variable expression that we deal with complex or just real numbers, right? Any number, they all obey those properties of the associative, commutative, distribution property. So no matter what you have, you can apply the property of distribution to it. Okay, so let's see. Here, let's just distribute. We've got 8x cubed minus 24x squared plus 2x, and then plus 2x squared minus 12x plus 1. Okay, so let's see. We've got 8x cubed minus 24x squared plus 2x squared is going to be minus 22x squared. Then 2x minus 12x is minus 10x, and then plus 1. Like that. Okay, now next, we talk about some special cases where we can have some formulas that can make it easier to do the multiplication. Now, but I just want to note, though, I want to stress here that this is really nothing to do with just polynomials at all. This is everything we're doing here, we're about to do here is all about the distribution property or the distributive property. So, or not the distribution property, the distributive property, right? The distributive property. But we know that all of these fundamental properties of numbers, the complex numbers and all real numbers and complex numbers obey them. So it doesn't matter what kind of sum of terms we've got. If we've got x to the 2/3 minus y, and we're multiplying that by whatever, 5x squared minus 3z, but these are just numbers, right? These are any numbers, and so that they all obey the property of distribution. It's not like we can only do this with polynomials or something like that. Okay, so you can do this with anything. And so, okay, but what are these special cases here they're talking about? Well, this is the case where we've got, I don't want to say binomials, but like we have two terms, because again, these can be anything. So a plus b, one term plus another term. Okay, so like a could be any expression, x squared y plus z, whatever, plus k to the 2/3. This is just a number. A is a number. And remember, a number can be, you can look at a number as an actual physical number, 5 or 3 minus 2i, or like a variable expression that's like a placeholder for a number. A whole variable expression, or just one variable. Okay, so we've got these two numbers here that we're summing, a and b. A complex number, real number, whatever. Okay, so what we want to think about is there's something that's related to this when we're summing two terms. Something that's related, like a kind of a cousin of this or a twin brother of this, is when you leave the a and the b in the same positions. The a is on the left, the b is on the right, but you just swap the sign in the middle. And what you have now are conjugates. These are conjugates of each other. This is a minus b is the conjugate of a plus b is the conjugate of a minus b. Okay, so like you might have heard the term complex conjugates, 5 plus 2i. The complex conjugate is 5 minus 2i. That's not just about complex numbers. Conjugates apply to any pair of numbers in any scenario. So like x to the 2/3 minus y squared, the conjugate would be x to the 2/3 plus y squared. Okay? So if we've got conjugates, then let's think about what happens when we multiply conjugates by one another. So if we multiply a plus b by a minus b, what happens? So let's do the distribution. You have a squared and then minus ab plus ab and then minus b squared. Well, minus ab plus ab goes away, and so we're left with a squared minus b squared. So like we start with a and b. Okay, if we're going to be multiplying the conjugate of a plus b times a minus b, then we can just square a and square b and then take the difference. And they call this the difference of squares. When you multiply conjugates, you get this difference of squares. Okay? Now what happens if we multiply either one of these by themselves? So what happens if we do a plus b squared or a minus b squared? Well, we've got a plus b times a plus b. So we'll get a squared plus ab plus ab plus ab plus ab. So that's going to be 2ab plus b squared. Okay, and if we did the same thing over here, we're going to see it's going to be a squared minus 2ab plus b squared. Okay, and so this, if you ever see something in a form like this, if you ever recognize a form like this, yeah, you're going to look at this. Most typically, you'll refer to this as a perfect square trinomial, but that's for the case where you're dealing with polynomial. A and b are polynomial terms. Okay, and you know, because we use this a lot with factoring. Factoring is about you're factoring polynomial expressions, and so we'll look for perfect square trinomials. But again, I mean, these properties this is just the distributive property, and so you can look for this kind of pattern with any expression, no matter what it is. This kind of form here, and you know that's it's just the sum of a square of the sum of two components of this, or the square of the difference of two components of this. Okay, so these special case products, we got the product of conjugates. A plus b times a minus b is a squared minus b squared. And then it's a square of a binomial. You get these perfect square trinomials, either one of these. But again, you can apply this to any types of terms. Because again, any algebraic term, any algebraic expression is a placeholder for a number. In the most general, it's a placeholder for a complex number, and all complex numbers obey the distributive property. And that's all. This is all based on the distributive property. Well, it's based on multiplication and addition, and the distributive property. But okay, but the complex numbers obey all of these properties associated with multiplication, addition, subtraction, division, and the distributive property. Okay, so let's work some examples here. Let's multiply these two binomials here. We can see that they're conjugates. We see that we've got a is equal to 2x and b is equal to 5. Right? A plus b, a minus b. So we know that if we just take a squared and then subtract b squared, that's going to be it. And there it is. Okay? Let's see here. These are also conjugates. You can see you've got a is equal to 1/3 c squared and b is equal to 1/2 d. A minus b times a plus b. The order doesn't matter. It's not like you have to put a plus b first. It doesn't matter. Okay, so what is a squared? That's going to be 1/9 c to the 4th. What is b squared? 1/4 d squared. There you go. Okay, now here, okay, we're squaring a binomial. We're squaring these two binomials here. So what it would be, so 3x minus 7 squared. So the a is 3x and the b is 7. b is not negative 7, it's 7, because the form we have is a minus b. We've got this, a minus b with a equal to 3x and b equals 7. So the perfect square trinomial for a minus b squared is a squared, okay, minus 2 times a times b. So minus, that's going to be what? 42x. And then plus b squared. There you go. Okay, let's see. The next one is, we're squaring a binomial again here, where we see that a is 5t squared and the b is 2v squared. And so we're doing a plus b squared. So this is going to be a squared is going to be 25t to the fourth, and then plus 2 times a times b. So that's going to be what? 5 times 2 is 10. 10 times 2 is 20. So 20 t squared v squared. And then plus b squared. So that's going to be 4v to the fourth. Okay, so now they give these kind of application examples, but this is just more multiplying polynomials. Like, what's the area of this rectangle? What there's a polynomial that represents the area of this rectangle. Well, that means we're going to multiply these two terms here, and then the volume of this cube is going to be x plus 3 cubed. So it's just more about multiplying polynomials. Okay, now next we're going to talk about multiplying radical expressions. Okay, but again, we're going to see those properties we just wrote out for the multiplying conjugates, etc. They apply to anything, any number. Okay, and so but also note that we could write these radical expressions in the x and the rational exponent form if we want, and it's all the same. But it's just the distributive property. It's they all obey that we just do distribution. So. Okay, 3 root 5 times 2, let's distribute here. 3 root 5 times 2 root 5 is going to be, let's see, you'll have 6, and then the properties of radicals, the same index, we get that. Then, let's see, we've got 3 root 5 times 4 root 2 is going to be 12 root 10, and then plus 3 root 5. Okay, so the principal root of 25 is 5. 6 times 5 is 30. Okay, root 10, 5 times 2, we can't simplify that anymore. And then 3 root 5, we can't simplify. Okay, now, but can we simplify this further? Well, remember, we look at radicals from the same perspective as like terms. Even though radicals aren't variables, it's a very similar idea in that you treat. You have to look for two radical terms that are like, which means that the coefficients can be different, but the radical itself needs to be exactly the same in every way. So like the same radicand and the same index, then they're like, then you can combine them. If they're not like, you can't combine them. So none of these are like, so this is it. This is as far as we can go. Okay, let's see. This 3 root x plus 5, and then 2 root x minus 7. So let's see, we've got 6, and then root x times root x is going to be x. Okay, then minus 7 times 3 is 21 root x. Then plus 10 root x, and then minus 7 times 5 is 35. Okay, so 6x, and now these are like radicals, right? Minus 21 root x plus 10 root x. The coefficients are different, but the radicals, they have the same index, same radicand, so we can combine those. Minus 21 plus 10 is minus 11. And there we go. We can't do anything more from there. Okay, now, but the next example, we've got these special case products, so like, look, here, 4 root 5, and these two are conjugates, right? Where A is 4 root 5 and B is root 6. A plus b times a minus b. So, okay, what's a squared? Let's see, that's going to be 16 times 5. B squared is going to be 6. 16 times 5 is 80. 80 minus 6 is 74. Okay, now this other example, we've got a two-termed expression squared. But that's fine. So one of the numbers is 3x. The other number is root 2. So we were doing a plus b squared. So the I don't want to say it's not a trinomial because we're dealing with, oh no, it is. Yeah, it's a trinomial because this is a polynomial. Root 2 is just a constant. So this is going to be a perfect square trinomial. So a squared and then plus 2 times a times b is going to be 6x root 2 plus b squared. And so you can see how that's a polynomial. You've got 9x squared plus 6 root 2 times x plus 2. It's just all x to whole number powers and constants.